Modern electronic equipment is complex. Its proper operation and repair depend on accurate measurements of current and voltage throughout the circuits. This requires the use of various instruments, such as voltmeters and ammeters. While these measurements are of value, they do not always tell us enough. In many cases, we must know how the voltages and currents vary. The voltmeter and ammeter can show these variations only at a very slow rate of change. Here is a voltmeter connected to a hand-crank alternator. When the crank is turned slowly, the meter needle is able to follow the voltage variations of this low-frequency supply. And we can see how the voltage passes through zero as it alternates between positive and negative maximum values. Now, as the cranking is gradually speeded up to increase the frequency, the needle oscillates more and more rapidly, but with shorter swings, until finally it comes to rest at zero. The meter's mechanical and electrical limitations do not permit it to respond quickly enough to follow rapid changes. Although the meter, at very low frequencies, shows that the voltage varies, it does not leave any residual picture of the changes, nor is it effective at higher frequencies. Even an AC meter, one especially designed to indicate the amount of voltage across an AC circuit, does not give a true indication of the actual voltage changes. Such meters show only the effective voltage value, not the peak voltage. A cathode ray oscilloscope, on the other hand, is the only electronic device which gives us accurate and instantaneous visual patterns of voltage and current variations. These patterns are called graphs. And two, because the electron beam which forms the oscilloscope patterns has almost no weight or inertia, it will respond instantly to the slightest variations of current or voltage. By measurement and comparison of these graphs or waveforms, a number of complicated electrical tests are made more simple and more accurate. There are different types and models of cathode ray tube oscilloscopes. All are fundamentally the same. The oscilloscope consists of a number of component parts and their associated electrical circuits. Let's see what they are. The vertical amplifier, the horizontal amplifier, the sweep generator, the power supplies, the cathode ray tube. One of the most important parts is the cathode ray tube. These elements of the tube are commonly referred to as the electron gun. When current is applied to the filament, a swarm of electrons is boiled off at the end of the cathode. Other elements in the tube, the control grid, the focusing anode, and the accelerating anode, act upon these electrons to hurl them in a small, sharply defined beam. This electron beam bombards the fluorescent screen to form a bright spot on the face of the tube. The intensity or brilliance of the spot can be controlled by varying the voltage on the grid of the tube. When the grid carries a small negative potential, the spot is bright. When the voltage applied to the grid is highly negative, the electrons are held back and no spot of light is formed. In some oscilloscopes, the beam can be cut off by means of a switch. In the off position, the grid bias is increased to hold off the electrons, although in all other respects the equipment is ready for instant use. A motionless spot on the screen may damage the fluorescent coating. When the switch is turned to the on position, the control grid is restored to the normal operating potential, and the spot appears. Now, let's look at the focusing control. It simply controls the voltage ratio between the focusing anode and the accelerating anode, so that the electrons are concentrated in a narrow beam. The proper use of this focusing control enables us to get a sharply defined spot. The position of the spot of light can be controlled by means of circuits associated with the horizontal and vertical deflection plates. In the cathode ray tubes of most oscilloscopes, the electron beam forming the light spot is bent by varying the voltage on the horizontal and vertical deflection plates in the tube. Here is a simple demonstration of the way in which the movement of the controlled light spot is used to produce a graphical picture of the characteristics of varying voltages. The side pin jack is connected to a horizontal deflection plate, and the upper pin jack is connected to the vertical deflection plate. Now, with a battery and a potentiometer, we apply a varying voltage to the horizontal deflection plates. Notice that as the voltage is increased positively, the spot is attracted in that direction. If the voltage is increased negatively, the spot is repelled. The same effect can be produced at the upper pin jack. In each case, an increasing positive voltage attracts the spot more and more. An increasing negative voltage pushes the spot farther and farther away. Rapid fluctuations in voltage move the spot correspondingly. At high speed, the persistence of the fluorescent screen plus the persistence of vision makes the moving spot appear as a line of light. The apparent extension of the line of light beyond the tube face is because it extends into the shadow of the shading ring. In the oscilloscope, the spot can be centered on the screen by these two controls, one for the vertical axis and one for the horizontal axis. These controls vary the amount of potential in their respective deflecting circuits. Now let's apply an AC voltage source to the vertical deflection circuits. Through these terminals, the signal passes to a simple voltage amplifier circuit. This amplifier, with variable gain control, connects to the cathode ray tube deflecting plates. The gain control on the panel permits us to expand or contract the vertical line of light. The horizontal amplifier circuit is fundamentally the same as the vertical. When we apply AC voltage to the horizontal deflection circuit, we can expand and contract the horizontal line. When the oscilloscope is used as a laboratory instrument, the voltage to be studied is usually applied to the vertical deflection circuits through the vertical amplifier. The horizontal movement of the spot of light is then controlled to form a pattern which can be analyzed and studied. A circuit of special character, in combination with the horizontal amplifier, produces a uniform horizontal motion of the spot. This circuit is called the sweep voltage generator. It moves the spot across the screen at a uniform rate of speed to furnish a time base. When the voltage to be studied and the internal sweep voltage are applied simultaneously, the pattern on the screen is a graph of the voltage in the vertical and horizontal plates. Now let's see how the sweep voltage generator works. This same circuit is sometimes called a sawtooth generator or relaxation oscillator. Here's a diagram of a simplified circuit. There are four main parts to this circuit: a source of constant potential, a limiting resistor, a condenser, and a discharging device. The condenser charges through the limiting resistor. When the charge in the condenser reaches a certain value, the condenser is instantaneously discharged through the discharging device. Then the cycle begins all over again. In other words, this gradual charging and instantaneous discharging of the condenser produces a gradually rising and instantaneously falling voltage. The waveform of the voltage across the condenser looks like this and is called a sawtooth wave. In most oscilloscopes, a gas-filled triode tube is used as a discharging device. This tube acts as an open circuit while the condenser is charging. When the voltage reaches a certain value, the tube becomes a conductor and the condenser is discharged. Since the condenser does not charge at a uniform rate throughout the charging cycle, the circuit is designed to use only the beginning of the charge, which is the most linear part of the charging cycle. When the sawtooth voltage is applied to the horizontal plates, the rising voltage sweeps the spot at a uniform rate across the cathode ray tube screen. When the voltage drops to zero, the spot instantaneously returns to its starting point. The frequency at which this cycle takes place is known as the sweep rate. That is, the number of times the beam is deflected per second. The sweep rate is controlled by two knobs on the panel, one for coarse adjustments and one for fine adjustments. Both knobs are connected into the sweep circuit. The coarse frequency control is actually a switching arrangement, which lets us substitute various condensers and resistors in the sweep circuit to get various charging rates. The fine frequency control is a variable resistor, controlling the condenser charging rate and giving us the intermediate values between the coarse steps. In some oscilloscopes, the coarse frequency control is calibrated roughly in cycles per second. The exact frequency desired can be obtained by using the fine frequency control. To study its characteristic patterns, a 400 cycle source is connected to the vertical amplifier. We turn on the beam, adjust intensity, and focus to get a sharp spot. Not too bright. Then, properly center the spot. Now, by means of the vertical amplifier control, we adjust the line of light until the pattern is the right size. Next, we adjust the horizontal amplifier to expand the pattern. This pattern is meaningless because the sweep rate is not yet synchronized with the 400 cycle voltage in the vertical plates. To synchronize the signal, we now adjust the coarse frequency control to the 400 cycle range, and then operate the fine frequency control until the pattern on the screen stands still, or nearly so, to give us a graph of one complete cycle. The synchronizer control is useful in synchronizing the sweep frequency with the frequency of the voltage in the vertical circuits. When this control is turned on, it feeds a small portion of the signal under observation in the vertical amplifier circuit into the grid circuit of the sweep oscillator. A little of this control goes a long way. Use the smallest amount necessary to get a stationary pattern. Too much will distort the waveform of the signal you're trying to study. We have seen what the screen pattern is like when the sweep circuits are exactly synchronized with the incoming signals. Here is the way the pattern looks when the sweep frequency is exactly half the incoming signal frequency. Notice now that two complete cycles or alternations are shown on the screen. Here, the sweep frequency is 1/3 of the signal frequency. 3 complete cycles are formed. As long as the frequency of the incoming signal is the same as, or some exact multiple or submultiple of the sweep frequency, the pattern will remain stationary, and the number of cycles will be in the same ratio. The synchronizing voltages which are used to stabilize the sawtooth circuits can be supplied from a number of different sources. We can select these sources by means of a switch called the sync signal selector. When the switch is on internal, the sawtooth oscillator sweep rate is stabilized by a portion of the signal in the vertical deflection circuit. Now let's turn the sync signal selector to line frequency. This setting synchronizes the sawtooth oscillator with the line frequency, or some multiple of the frequency supplied by the power mains. Now, on the screen, we get a direct frequency comparison. The number of cycles on the screen shows the frequency ratio of the signal being compared to the line frequency. For example, supposing the line frequency is 60 cycles, we set the frequency to 60. If we have 3 complete sine waves on the screen, we know that the frequency of the test voltage, as shown on the screen, is 3 times the line frequency, or 180 cycles. When the switch is set to external position, the horizontal sweep circuit can be stabilized by an external frequency. Each type of oscilloscope is provided with some switching arrangement to disconnect the internal sweep. This permits us to apply any external potential generator directly to the horizontal amplifier without passing through the sweep voltage generator circuit. Since the linear sweep voltage generator is no longer in the circuit, applying an AC voltage simultaneously to both horizontal and vertical plates results in a pattern having no linear time base. These are called Lissajous figures. When linear time base. These are called Lissajous figures. When we use the same frequency for both vertical and horizontal deflection circuits, the shape of the pattern depends on their phase relationship and the relative amplitude of the varying voltages. Varying the amplitudes of these in-phase signals will vary the angle shown on the screen. For example, here is the pattern produced when the signals in both sets of plates are in phase and of equal amplitude. Notice the 45-degree angle. This animated diagram shows what is happening in the circuits when the 2 voltages shown are applied to the vertical and horizontal plates. Here is another pattern. This one is produced when the voltages on the horizontal and vertical deflecting plates are of equal amplitude and frequency, but are 90 degrees or 270 degrees out of phase. If 2 different frequencies are applied to the 2 different sets of plates, we get another type of wave on the screen. This figure, for example, is the result of a frequency ratio of 1 to 3, with the horizontal and vertical voltages 90 degrees out of phase. Even complex patterns can be analyzed by graphical methods. By reference to standard charts, frequency determination, phase relationships, and many other characteristics can be determined. We have seen the general principles on which the cathode ray tube oscilloscope operates. Now let's see it in actual use. Here, laid out on a breadboard, are the simplified circuits of a power supply unit. This unit draws 60-cycle alternating current from the power lines. The unit consists of a transformer, rectifier, condensers, choke coil, and load resistor. It delivers an almost pure direct current, which can be used to power many types of electronic and radio devices. Let's hook up the oscilloscope to make a complete check of the power supply unit. The signal input leads of the vertical plates are connected across the primary side of the transformer to see the waveform delivered to the transformer primary. It is the 60-cycle sine wave. Next, we'll check the secondary of the transformer. Notice that the enlarged waveform shows the step-up ratio of the transformer. Now, let's move the oscilloscope leads to check the voltage output after it has passed through the half-wave rectifier. The pattern on the screen of the cathode ray tube shows that the negative portion of the alternating current wave has been stopped or cut off by the half-wave rectification. This produces a pulsating output voltage which varies from 0 volts to maximum 60 times a second. Let's hook up the transformer and rectifier to get full wave rectification and again check with the oscilloscope. The pattern shows that we are using both halves of the alternating current wave and that our direct current now pulses 120 times a second. Next, let's check the output on the other side of the filter condenser. The screen pattern shows that the condenser tends to smooth out the pulsations. Let's try the same hookup with a larger condenser and compare the screen patterns. The larger condenser has reduced the pulsation even more. Next, let's move the oscilloscope leads so that the choke and filter condenser circuit is included in the hookup. The pattern shows that the voltage has been rectified and smoothed to almost pure DC. In the same way, we could add another choke and condenser to the hookup until the output is perfectly smooth. Here is the way the screen patterns might look. By knowing what waveforms to expect in various circuits, the skilled oscilloscope operator is able to check through and locate faulty sections of power supplies, audio, radio, and intermediate amplifiers, and other more complex circuits. Let's apply this idea to checking an audio frequency amplifier for distortion. Here is the waveform of the original audio signal. Compare it with the waveform taken off the first stage. In spite of the increase in amplitude, there's little distortion at this point. Here is the comparison of the first stage with the second stage output. Here is the pattern of the third stage. Comparison of the waveform at this stage with the previous one shows distortion. And now that we have found the trouble to be in this section, it's a routine matter to track down the cause and eliminate it. A final check with the oscilloscope concludes this demonstration of one of the innumerable uses of this instrument. The unique characteristics of the oscilloscope, visualization, instantaneous response, and a wide variety of uses in many fields, limited only by the ingenuity of the technician, make the oscilloscope an indispensable tool in the field of electronics.